So the agenda will, for today, when we are going to talk on DPC++, most of the time will consist of two parts, and I finished each part with some kind of demo or lab, which you can, if you want, you can try yourself, because it's quite easy one based on the Jupyter notebooks in the dev cloud, and I will show you how to log in there and how to proceed with the exercises or labs, and I will show it definitely myself as well. So it will consist of two parts. One, it's interesting that when you're trying to present DPC++ or SYCL, it's not so easy to find a good structure to show it. In principle, all material can be divided into four big chunks, which is explained in the SYCL standard, and it consists of a memory model of a SYCL, kernel model, execution model, and that's it. Actually, we have four models, right? Doing it in this way is usually not so easy to understand, because in that case, you cannot get a real example of a code in front of your eyes. My approach is more based on one simple example, like hello world in the GPU world. And based on that, we will cover most of the topics. And the next step will be more focused on the Intel extensions, which are already a part of a SYCL standard, like unified shared memory and subgroups. By the way, can we run a poll right now so that we can collect some interesting, yeah.
So here's a poll from Igor.
Yep.
Please answer if you like.
Okay, quite a lot of people already voted, and this is very nice. And I can see that, yeah, most of you are already experienced in heterogeneous programming, like 70%, which is very nice. And I will keep this in mind while presenting. But for SYCL, almost 90% are still new, and yeah, this is a very good learning for me. So fine-tune the level of details. I will go. Yeah, here's the results. Okay. So now let's go and talk about DPC++ in more details. I think you've seen this slide many times, so I don't want to duplicate a lot, but the core concept is data parallel C++ is not a new language. It's actually a C++, and this fact you need to keep in mind, because it's different from, let's say, CUDA approach, where you have new keywords and you really cannot compile it with any other compiler except NVCC, right? Here, the concept based on pure C++, so theoretically, you can use any open source, well, not even open source, any C++ compatible compiler to compile your host code. For device code, it will be still a challenge, but I will go in more details while addressing compilation and execution flow of a DPC++ application. So note, there are no new keywords in DPC++. And one more remark about DPC++ and SYCL. DPC++ is based on the SYCL standard, which means it is the implementation of a SYCL standard. But on top of that, since we identified some gaps in the features, right? We want really to improve the SYCL standard. And that's why on top of that, we're implementing the extensions, which are specific to data parallel C++ at this moment, but the goal of these extensions to be included to the SYCL standard finally. So again, it is pure C++ code. It is based on a SYCL standard, And on top of SYCL, it has some extensions, which we identified as a critical. And we are always open to hear your feedback in case you feel like something is missing in the standard. We're always looking for this kind of feedback to introduce some great new feature as an Intel extension and then as a part of a SYCL standard finally. So it's always our goal. There is no goal to make our compiler having some features which are not in the standard. Our final goal is to enhance the standard itself. A few words about implementation. So we are implementing our compilers, and almost all parts of compiler architecture is implemented in the GitHub open source project. So the compiler is based on LLVM framework, and front end is CLang based. And you can always go to this repository and take a look on the sources of a compiler itself. However, when we are talking about compiler, you need to know what it may consist of different parts, right? For example, we separate a compute runtime, which is required for the runtime, but in some sense, it is still a part of a compiler, because for DPC++, the compilation doesn't happen in the way like it happens for CPUs. So for DPC++, you have an option to make a JIT compilation, and in that case, DPC runtime is doing this at a runtime. So in reality, there are three projects which should be important for you. One is definitely LLVM Intel implementation, right, which has a SYCL compiler, DPC++ compiler available there. It is a compute runtime which has OpenCL and level 0 runtime, also available in open source. And the third, which is not listed here, but it's still important, is a device compiler. So for Intel targets, we do have an open source project called IGC, Intel Graphics Compiler. These two links will be very useful for you. So to take a look on how you can code. So we will cover only basic stuffs in the presentation, but if you want to see all the use cases which you can apply to your code, I would really recommend to go to the oneAPI samples, and we will use it in DPC++ compatibility talk a bit, showing how you can use it. But I would also recommend this link, which has a SYCL standard conformance tests available there. And you can browse through the hierarchy of these tests and find a lot of useful ways. So for example, there are some code samples showing how you can use function pointer in device code, which is not allowed by a standard, but which is very nice feature which you can use. So there are many very interesting tests there. I will probably in the demo I will show you the content and show what is can be interesting for you. So now a few words about SYCL standard. Again, when I will talk about DPC++, by default, I mean that it is a SYCL code. So if I'm talking about DPC++ code, it means it should support all the SYCL features. But there may be some features in DPC++ which are not in the SYCL standard. So the latest standard was released in February this year, so it's really fresh, and there are any single compiler which supports it, right? Which has 100% conformance with SYCL 2020. But since we were influencing it a lot, we have already many major features implemented in DPC++, which are part of SYCL 2020. Overall, there are more than 40 new features in the SYCL 2020. And if you're familiar with SYCL 1.2.1, then I would recommend to open this link and go to the latest section. It's Appendix D in this specification, which showing the difference between SYCL 2020 and 1.2.1. Because there are some major differences, and I will try to highlight some of them during this presentation. The difference is not in the sense of additional features which you are getting, like unified shared memory, subgroups, reductions, and so on. But there are some features removed or replaced with something new in the SYCL 2020. For instance, host selectors and host devices are changed significantly and reworked. This slide is showing our intention, and I tried to list some extensions which we implemented last year, so quite a long time before SYCL 2020 was finalized or even published. And you can see some of the major extensions. If you go to this link, you can find all the extensions in our Intel LLVM GitHub project. And we have more than 40, I guess, there are two extensions. And this major one, actually, as you can see, they were approved and accepted in the standard. I intentionally left a few which were not, just to show the idea of what is approved and accepted in the SYCL standard in the first wave and what will be probably accepted a bit later. And the main reason is if you can see a feature which is applicable for any target device, so not only CPU or GPU or FPGA, but it is a useful feature for any target device, then in that case, the standard committee is willing to accept it with a higher priority. In this case, this feature, which is called pipes, which improves spatial data flow support for FPGAs, is something very limited to FPGAs. And argument restrict was not also accepted in the first wave to basically for the same reason, I guess. It was more or less focusing on CPU optimization at that moment. But all our extensions are, and we are looking forward and working to add all our extensions back to the SYCL standard. And we also have some plans on long-term plans in order to work with a C++ committee and incorporate these features later to C++. So this is a long term. Yeah, if you have any questions on that, just unmute and I will be happy to address. So this is a summary slide of Intel compiler. So I've seen that many of you already used Parallel Studio XE in the past, right? Any question on the bridge?
On the chat, there's a, I think, important question, and some are pointed that out. If one uses DPC++ now, is there any hope it will still run in 5 years and it is not deprecated?
Okay. The question here is that, is it really a question of on SYCL, or is it a question on DPC++ and our strategy? So our strategy is really long-term, and at this moment, we don't plan to deprecate anything. Regarding SYCL, I think it was on the market since, I don't exactly remember the year, but I guess it's already here for quite a long time, relatively long time. Of course, not like oneAPI standard, but yeah. And I don't believe that the SYCL standard itself will disappear. And if you take a look on the ecosystem of a SYCL, then DPC++ is not the only available compiler at that moment. So there are 3 other implementations. One is from CodePlay, which supports, by the way, many other target devices. So which supports a lot of different devices. It's also a HipSYCL, which also can target different devices in comparison with DPC++. So the idea here is that if you write your code in accordance with a SYCL standard, then you shouldn't even care about availability of a DPC++, right? Because then you can switch to any compiler anytime. But we don't have any plans to deprecate this, and our focus is to work on that and improve. And in based on the situation in the world today, I would not estimate or speculate on what may happen in 5 years, right? So we even don't know what may happen next month or next week. The current situation, unfortunately.
Now, the concerns, if I take a comment from a chat, is relevant in the sense that, of course, large software projects stay for many decades, and then the core developer have to make decisions how to go in the future. So I think that's the background of the two questions.
Yeah, I think yeah, it's a valid point. I think you should be based on the standard SYCL standard, and I don't think that you'll have a problem in that case. But if you really if you want to be more focused on something more mature, right? Well, because in terms of features, DPC++ gives you a lot of useful features. But if you want to have more mature standard like oneAPI, you can also do this. So we also provide an alternative for those customers who prefer oneAPI to do that. So it's your decision finally, what do you want to get? But I think that you shouldn't think about DPC++ in that way, that there is a possibility to disappear and so on. Okay, let me go back to the slide. So we do have now, actually we do have now two different compilers. So one is Intel Classic compiler, and Intel Classic compiler has our own front ends and back ends, right? Closed source. In case of ICC, it's partially true because for ICC we're still using the front end, the compiler front end, which is EDG Edison Group based. And these are classic compiler, right? This is what you have been using in Parallel Studio XE. The next generation of a compiler is based on LLVM framework and on CLang as a front end.
Igor, yeah? you need to share your slides.
Something happened? So
yeah.
Sharing, okay.
I thought it was by intention as we started with the questions.
No, let me share it then.
Okay, thank you.
Okay, can you see it now?
Yeah.
Okay, I was highlighting the two parts. Okay, so then, so this is our classic compiler, and these are our LLVM-based compiler. So if you see the X at the end of a compiler driver, then it is a new modern LLVM-based compiler. What does Intel compiler driver name mean? So this ICC, DPC, PP, ICX, etc., these are compiler driver names. So these are not actually the compilers. And the compiler driver is a part of a compiler which parses the options you are passing, right? So it's usually the command which you are used to invoke the compiler under the hood. But these compiler drivers can provide you with different set of features. For example, the difference between DPC-PP and ICX is that in case you invoke the compiler with DPC-PP driver, there are some compiler flags and paths preset, which are not in case of ICX. For example, -f-SYCL option, which shows that the code you're trying to compile is actually the DPC++ code or SYCL code, and that you need to compile the device code and host code. We will go in more details on that. At this moment, you just need to know that we do have different compilers, and you have a variety of choice on what to do. My own recommendation would be for the best performance of a CPU code or host code, right? You can still use our classic ICC and i4. Since all the compilers are cross binary compatible and linkable, you can do a lot of stuff. So for example, you can compile your Fortran code and you can invoke some kernels which are written in DPC++ from your Fortran code. What you can also do is you can write your Fortran code in the and compile it with classic Intel Fortran compiler, which is highly optimized and quite stable, right? And you can select only a few modules of your Fortran code, which has oneAPI offloading. And in that case, you can link all together, and it will be also using heterogeneous programming and GPUs in your case, right? And on that, tomorrow Michael Steyer will present you some nice talk about using oneAPI with Fortran for doing offloading, right? So you can do it in the different ways, and this compatibility and the option to link all together, it's something which you can utilize today, and this is what I would recommend to you if you are looking for a greatest performance. These are the links to get the base and HPC toolkits, so you can try it anytime as you wish. And as Michael already was talking earlier, we do have a dev cloud where all the tools are pre-installed, so it's unbelievably easy to get an access to the latest Intel hardware and software nowadays. And we really improved here, and it takes only like 15-20 seconds to get an access to the dev cloud. In order to avoid additional questions, I want to state this in the beginning. So from the list of devices we support at this moment, it's definitely all Intel hardware, right? Like Intel CPUs, Intel integrated graphics, discrete graphics cards, and FPGAs. But there is also support of NVIDIA hardware, which was implemented by CodePlay. The only important note here is that the support is available only in open source version of a project. So if you will get the toolkit using the links I provided earlier, you will find only the support for Intel hardware there. And for NVIDIA, you need to go to the open source project, you need to compile a project, and then you can target any device, including NVIDIA hardware and Intel devices. I'm working right now on making it possible to use the so-called CUDA backend of a DPC++ compiler together with oneAPI toolkits, which should increase and make it much easier from usability point of view to switch between different vendors and backends.
Igor,
yep.
There was a question in the chat on the previous slide, what the star means at GPU with IFX. So last line, the star at GPU.
Yeah. There is also a star on FPGA. So yeah. I don't think there was any spatial meaning here. I don't exactly remember how it how I put it here. Maybe it's more yeah. So I don't exactly remember why. You can simply ignore it. So in reality, it has a full GPU support. What you need to know is that yeah, I think probably it was derived from an older version of the slides where we have some kind of a beta support for GPUs, but yeah, don't really mind on these stars. I just want to highlight that for IFX, we position it in the toolkit, and it's available, as you can see, in HPC toolkit. So if you download base toolkit, you will not find it there. So it's only for HPC toolkit. it is positioned as a beta compiler at that moment. So this is the only compiler which has a beta quality at this moment. And one important note here, maybe, so it's good that we are back to this slide, but but I cannot talk too much on why the asterisk is here. But the important note is here that our toolkits are designed in a way of a plugin. So base toolkit is a basement of any other toolkit you want to install. So you always need to start with installation of a base toolkit and getting, for example, these compilers, DPCPP and ICX. And in order to get additional compilers, you need to download HPC toolkit and install it on top of a base toolkit. So don't start with installing HPC toolkit as a standalone package. It's really some kind of a plugin which you need to install on top of a base toolkit, which is important.
There is another question. Sorry for interrupting you.
No, it's really good that we have a so lively discussion, and that was the intention. So,
is the IFX compiler included in the Visual Studio integration?
Yes, it is. So our integration supports all the compilers. So you can invoke an IFX compiler from the Visual Studio as well.
Okay, thanks. And
this is a slide just like an advertising of what Michael Steyer will talk about later, but is that oneAPI offloading is actually supported by the compilers only based on the LLVM framework, so only with ICX and IFX. And in order to enable oneAPI support there, you need to enable this FI oneAPI option. So pay attention to this I, because fopenapi itself will use the implementation of a C-lang, open source C-lang implementation of oneAPI, which is not optimized so well. So it's just a spoiler of what will be presented to you tomorrow. And for more details, you can also in advance go and read on what is supported from the oneAPI offloading perspective. So I think this is a first quite important part of a presentation which we passed. It's more about basic concepts, our intentions, and the compiler availability and where you can get it. So now we will deep dive into the basics of DPC++ language itself. I really like what you're asking the questions. I think it's you already asked very nice and interesting questions, and I encourage you to keep doing this, since it is quite important for me to hear your feedback and explain all the topics. So first statement, that DPC++ is the implementation of a SYCL standard, right? So all these terms which we are going to use today, these are coming from the SYCL specification. And they're actually derived from a SYCL 1.2.1 specification, most of them, not from SYCL 2020. And you need to keep in mind that SYCL 1.2.1, the older standard, it was purely based on OpenCL. So by standard, it was stated that it's abstraction over OpenCL. Nowadays, SYCL 2020 is not, and it allows you to use any backend API. So it can be not OpenCL, it's one of an example, but it can be any other lower level heterogeneous API like level 0, which we have in oneAPI initiative, or even CUDA API still can be used as a backend of this. So think about DPC++ as an abstraction model. So you're writing on the high level abstraction, and then it is the task of a compiler and runtime to map this code to an underlying lower level API. So once it was based on the OpenCL historically, there are many terms which are coming from OpenCL, and one is a platform model, and the platform model means that it is actually specifying the host which is controlling one or more device and the device. And this is how the regular DPC applications looks like. So you have your host code, which is running on CPU, and you have your device code, the device code organized in the form of common groups. So these common groups are submitted to the common queue, and this common queue is usually linked to a specific device. So in your code, what you're usually doing is you're creating the queues and you're submitting common groups to this queue in order to execute. And note that you need to keep in mind the architecture of a target device. And if you're going to fine tune the performance finally for some target device, when in most cases, you need to care about it, right? Because by standard, the device can be any device. It can be FPGA, GPU, or any, I don't know, device architecture which can be available in the future. But since the architecture of these devices may be so diverse, then it's almost impossible to follow the concept right once and get the maximum performance. So what DPC++ guarantees you is that you will be able to compile your code and to run your code on any device. If you want to get the maximum performance out of this code, then probably you will need to do some fine-tuning based on the target device you would like to use or you are planning to use, right? So it's very important. So that functional portability is guaranteed, but performance portability is not, and I would say it's not possible in the existing world with the diverse architectures which are so different, even from, for example, from memory hierarchy point of view. A few terms, terminology used in DPC++ and SYCL applications. So this is an example of a real code. This is a very simple one, right? Like hello world in heterogeneous programming, which performs vector addition inside. Again, if you take a look on the syntax itself, it is not, it doesn't have any new keywords. So all it does, it just include the header files with the definitions of classes and APIs. And then you are free to use these APIs inside your code. And it's implemented in the way of templated library. So once you included the header file, you can use these classes as you wish. We'll go into more details on each of these lines, but I want to highlight that if you take a look on the SYCL code, then you need to be aware on how to recognize the device code, which is going to be run on the device, and the host code, which is which you are running on the CPU. And there are two markers here. So as I said, the basic concept is that you're creating the queue, which is linked to some device, and then you're submitting the common groups to this queue. So the first step, which you need to pay attention, is how the queue is defined, and then pay attention to the submit operation. So the submit member function of a class queue. So this is doing the enqueuing of a queue. However, all that is defined until this parallel for invocation, it is still a host code. So it's not executed on the device. The next marker for you to recognize the device code and the kernel is this parallel for invocation. It will be not parallel for all the time. It can be also our method to invoke the kernel, but in reality, in 99% of the case, it will be parallel for. So again, to recognize device code, find the queue submit operation and find the parallel for. So inside parallel for, this is really a code which will run on your device. This is a kernel. And DPC++ actually has a class called kernel, and in that case, it's implicitly constructed by runtime. So it's only a terminology. We will go into more details later. And I sometimes you will see that so there is a host code and device code, and definitely you need to understand that you will need a compiler, different compilers for host and device code, right? But sometimes it's also important to separate the scope. So there is an application scope, and this is a scope of maybe it's better to start with a common group scope. So a common group scope is everything which is declared inside the queue submit, but before we have a parallel for. This is a common group scope, and there is a device scope. So this is a scope in your application which is inside your device code. So everything else is called application scope. And you need to know this separation because different features of SYCL and DPC++ can be used inside this scope. So for application scope, you can use any C++17 features and with no limitations, right? Inside common group scope, you still can use it since it's still a host code, but there are some SYCL features which you can declare only within this common group scope. For example, if you want to use the shared local memory and then create the local accessor, then you can do it only in the common group scope. And the device scope has quite many limitations of a language which you can use. So when we are talking about the support of C++17, right, as a natural support based on the SYCL standard, we are talking of this support in terms of application scope. But inside device code, there are quite many limitations. For example, you cannot use dynamic polymorphism. However, you can still use templates. You can use static polymorphism. There is no exception. Exceptions, so you cannot work with exceptions inside this code and so on. So there is a list of limitations you have inside the device code. In the past, it was not possible to use function pointers. However, we do have extensions which allow you to do this and so on. So just keep in mind that not all C++17 features are possible inside the device scope.
Igor?
Yep.
Just one quick question. The one beautiful feature of C++17 that you are using in the application scope here, the CTAG, I think the buffer is a template, a class template.
Yes.
That you're using
CTAG.
Yes. Is that available in the device scope?
That's a good question. I haven't tried, but I think so. Yes, since the limitations are basically more based on the nature of a devices itself.
This is just template and it should
yes,
be
but
available.
templates and CTAD, template argument deduction feature, it doesn't really affect this. So I think yes, you can use CTAD inside the device code too. Right.
Another quick thing, could you point out where the data copy is happening between?
Yeah, I will. Yeah, it's a good question, and I will cover it later.
Yeah. Igor, yeah. There's a question on the chat. How does parallel for accelerates the execution?
Yeah, we will address this further. So it's only a terminology and the parts of the application. So I will address both these questions in the following slides. So let's start with more details on the implementation. So how do we actually write our code? So on this slide, you can see that we put additional scope here, and I will explain a bit later why, but it's not mandatory. So in reality, you can keep writing your code. So once we have our data available, right, you can see it's a vector here, but you can use plain arrays and the pointers, it doesn't matter. So what the standard expects you to do as a first step is to actually create a buffer, create a queue. I would start with the creation of a queue first. So the queue is a way how you can link to a specific device. In reality, under the hood, it's not only queue class, which is constructed where. So there is also a device class, a device selector class, and the context class, which are created. And you can always explicitly choose this. But on the high level, queue allows you to link to some specific device and to then submit the tasks, submit the command groups to execute on this device. It doesn't matter if you start with a queue or if you start with a buffer creation in that example. So I'm here with this hello world sample. I'm only showing one memory model, which is called buffer. And there is also an alternative, which is called USM, which I will cover a bit later. So you can also start with creation of a buffer. So the idea is that in order to copy the memory back and forth from host and device, right, you need somehow to wrap your initial data to additional container. And what we're doing here is we're separating the storage of the data with creation of a buffer class with access to this data, to this initial data inside the kernel. And you will talk in the next slide on how it's implemented via this accessor mechanism. So once we wrapped our data with the buffers, we cannot anymore modify this initial data. So here, if you will try to write to a vector A, B on C, the behavior is unexpected by the standard. Once you created the buffers, you need to operate with the data only through these wrappers. Once you destruct the buffer class, then you can operate with initial original arrays of vector or any data you are using. This is an important note here. So as I said, we are separating the storage of the data and access to the data. And this gives us a very nice feature I will talk a bit later. It will allow the runtime to care about possible data races and data dependencies between kernels and between common groups. So here, once we created the buffer, we are invoking a get access member function of this class, and we are creating accessors and specifying explicitly. You can see here the handler to the common group, and we are specifying the mode in which we are going to access the data inside parallel 4. So here we are specifying that we will read A and B and we will write to C, which means that we can track the dependencies of these kernels with any other kernels. So let's now talk a bit more on that. So there are basically, in accordance with the SYCL 2020 standards, there are two main approaches. One is called this buffers approach, where you're using the abstraction with this buffer. So you're wrapping your initial data to one more layer of abstraction. And there is also a unified shared memory approach where you keep working with pointer-based programming. So both have benefits, advantages and disadvantages. There is also a corner case of buffers, which is called images, but the approach with images is similar to a buffers. So it's still the abstraction, it's still one more container, it simply has extra functionality for image processing. And this, by the way, will be quite extensively reworked in the upcoming standards, because there are many gaps which we want to hide or implement finally. So these two approaches, now we are talking about the buffer memory model approach, and we will address unified shared memory a bit later. So, and with the buffers, as I already shown on our Hello World application, we are wrapping our initial data to some kind of a buffer, right? In that specific case, we even don't do that. So you can see that you can create a buffer which is not attached to any data, as you can see here. Note that all the classes in the SYCL are templated. And as I said already, it is implemented in the form of a templated library. So if you're not using C++ 17th feature CTAD, which allow you to avoid the specification of template argument explicitly, then once you create a buffer, you need to specify the data type you want. And there is also actually a dimensionality of the buffers. But in this example, we are creating two buffers with the ranges. We are creating the queue, and now we are creating accessor here in a bit different way, right? So we don't invoke the get access member function, but we are creating, we're constructing it explicitly using the constructor. And the example here shows that you actually may have many different submit operations, right? You can submit different common groups to the same queue, and in that case, it is possible that there can be a data dependency, right? For example, in this case, in both kernels, you're writing to the out array, and in that case, you need somehow to catch this dependence. And the main reason, or one of the main reasons why this buffer accessor approach exists is that it allows runtime to track and catch this automatically. So you don't need to care about it. You simply defining your buffers and creating accessors and specifying the data access inside the common groups. And which allows the runtime to create a graph of dependencies at runtime. And the node of a graph is a common group, and the edge is actually this accessor dependency, write or read. So in that case, a specific case, we create one kernel and two kernel, and there is a clear dependencies with the data here. So the kernel 2 will be not executed until kernel 1 is finished, and it is done automatically by the runtime.
Excuse me, what
Yes.
was the type of the IDX thing in the previous slide?
Here?
In the parallel for?
Auto, you mean this?
Yeah.
It's auto, so you can
No, that's fine. But you see, it's used as the index on the left-hand side, and it has an index operator on the right-hand side in the next line.
Yes, so you're assigning, so you're writing to the array just the index, but I think it's not IDX 0 here. It's maybe, yeah, probably it's not, this is not allowed operation. I don't think this is available.
Okay, thank you.
But IDX is just an index. So if I think that this operator is only available in the item class and not IDX. So in this particular example, the class was ID, and yeah, I think it's a good point here. But the intention of this sample is to show how to fill the array with the indexes of work items inside.
Thanks.
So again, when you write auto, and when you and when you have a range class, then this auto will be ID. And that's, by the way, this is a very good question, because it shows that sometimes usage of these C++ 17 features like auto type or template argument deduction is not so great, because you are missing some part of understanding of the code itself. So you don't know what the actual type is. So from the way how you program, it's so easy, but from the understanding of the code, it's not so easy now to get what is the type of index I and what you can do. So we created the buffer, we created the queue, we are doing the submit operation, and we created an accessor. So now we are fine to invoke the kernel itself, to enqueue the kernel, and we are doing it via the parallel for member function. You can see here that we always invoke the methods with a handler to the common group, which means that this common group object, it does have information on all the accessors here, and the parallel for method is also invoked. So it's a method of a common group handler, actually. So in this very simple naive example, we are simply passing the iteration space as a constant integer, as a first argument, and we're passing the lambda function as a second argument. And this lambda is actually our kernel. So this is a function which is expected to be executed on each execution unit on our target device, or on each thread of a target device. All this terminology is derived from OpenCL actually, and we will go in a bit more details later. Actually, implicitly, the range class would be constructed here, and for this outer, the ID class would be constructed. And let's talk a bit about these ranges and ID. So with ID, it's more or less clear. It allows you to identify individual thread or work item of a code. So it helps to identify the individual piece of the data for each kernel invocation and execution on each thread. The range is actually specifying the iteration space over each you want to execute your kernel. I want to highlight that there is actually a difference in the syntax which is used in SYCL 1.2.1 and 2020. And the difference is with the old syntax, it was not possible to use C++17 feature to deduct the arguments passed to the template. So based on this original SYCL standard, you always need to specify the data type, and you always need to specify the dimensionality of a range. And same for ID class, which helps to identify the individual instance. And this is quite important because it helps you to understand what is actually passed and what data types are used. So actually, our compiler is backward compatible. So if you are writing on SYCL 2020 syntax, it works fine. But if you still continue to writing in SYCL 1.2.1, it will still work fine with DPC++. One important note here is that in the initial example, I haven't seen this class explicitly specified for parallel 4. And this can be sometimes quite useful to do, because this will say to a compiler to generate this specific name for the lambda, which we are defining here. So in that case, if you're going to use any profiling tools like vTune, then you will have you will see your profiling data, which will have a meaningful name like vector add, for example. So it quite often makes sense to do this explicit naming of a lambdas inside. But this, it was an extension in DPC++ called unnamed lambdas or named lambdas. So these extensions allow you to avoid the explicitly specification of a lambda as a parameter to parallel 4. So as a summary, in this way of invocation of parallel 4, we are passing a range as an argument, which is actually describing the iteration space of parallel execution, right? We are using the ID class, which will allow you to index the individual instance or work item. And you can also, as an alternative, use the item class. And the question that was earlier, I think in that case, the sample was based on the item class, but I think it's a wrong one, sample. So item also represents an individual instance, but it provides some additional functionality to query properties of a range like get ID, get range, and so on. So these are two different ways how to identify individual work item or thread inside the kernel code. But it's a quite naive way of using, because in that case, with a range, you cannot control a division, a further division of this range into a smaller chunks, which is actually happening all the time. And I will go into that right now. Yeah.
Igor, can I make ask you? There are some questions from the chat. One is regarding the maximal depth of the SYCL graph. If that depth is reached, will be the main thread then stalled?
That's a good question. I haven't seen a case when we can reach this kind of limitation of a graph. So I don't expect it's so easy to reach it. So I don't really know what will happen in that case, but I think, let's say in this way, if you will have a reasonable example showing this case, it will be really nice to investigate it. So I don't think you will be able to to hit this case.
Okay. Second question is, are there execution policies for parallel for like in C++ 17?
No, the execution policies is more applicable for PSTL, right? So for parallel for, we don't have these execution policies. It's it's a way how you implement the parallelism in DPC++. We still have PSTL available as a part of oneTBB, where you can specify the execution policies, but it doesn't allow you to specify the execution on GPU yet. But for the idea here is that you specify the execution policy via the queue, let's say in this way, more and in more implicit way, because once you create a queue, then you link to some device, and then you execute on this device by submitting a command group to this queue. So.
Okay, on the previous slide in the examples, the question is, does the current code vectorize as
yes,
you're using float or not float for or something as a vector data types?
Yeah, the kernel code is expected to be vectorized, and this is quite critical. And depending on the target device, it can be or cannot be vectorized. But yeah, we will talk on subgroups a bit later on how you can benefit on that. But by default, the compiler is trying to vectorize the device code. Yes.
And then I think it is a comment that the class feature you mentioned on the previous slide, also slide 21, was class not feature of the SYCL one-to-one specification.
Yeah, exactly.
Right?
That's what. Yeah, that's exactly. It was not a feature of SYCL 1.2.1. That's why on this slide, I wrote this. So I explicitly wrote this because if you will avoid it, then the compiler, which is conformant with SYCL 1.2.1, will issue a compilation error, like the lambda should be named, and this was a feature introduced as an extension originally in DPC++. So you are passing the fSYCL unnamed lambda option to the compiler, and it allows you to avoid this explicit template argument.
From the same person, just a comment that this feature was already included in other SYCL implementations like TriSYCL.
Yeah, but I don't think it was, let's say, in Compute CPP, for example. So for in Compute CPP implementation and CodePlay implementation, it was not there. Yes.
Okay. Go ahead.
Okay, so now let's talk about thread hierarchy and how does it map to the underlying hardware. So unfortunately, there are some limits in the underlying hardware, right? So we cannot create a range of a size which we want, and it cannot map to the underlying hardware because it has some limits. It has a limited number of execution units, and the underlying hardware, usually, if you're talking about GPU, right, it consists of some in case of Intel, it consists of slices and subslices, so of some logical division of resources into the groups. And that's why, from the software point of view, from a programming point of view, we need to have an option how to map to it in order to avoid inefficiency of the code. And that's why in SYCL, there are different terms introduced. The first one is a work item. So, and the work item represents a single thread within the thread hierarchy. So then these work items can be also grouped into the subgroups. And in that case, it represents a short range of consecutive threads. And these consecutive threads can be processed together as a CMD vector. So this is usually linked to the CMD approach when we are talking about subgroups, but it allows you even more than simply vectorization. It allows you to avoid additional synchronization and so on when you're operating with a subgroup. So it's very powerful way how to fine-tune your performance. This, by the way, was also not a part of a SYCL 1.2.1, so it was introduced in SYCL 2020. It's available as a DPC++ in DPC++ compiler. Workgroup is a 1, 2, or 3-dimensional set of threads, and note that synchronization across these work items inside the workgroup, it's only possible with barriers. And you cannot synchronize work items from one work group with work items from the other work groups. So, and finally, we are constructing the ND range, which is a dimensional grid of work groups, right? It represents the global range and the local range of each work group. So actually, ND range consists of these blocks, which are called work groups, right? And in the approach I was showing earlier, when we create in this hello world, we create implicitly a range class. It doesn't actually construct the ND range. So well, we don't do it ourselves. So it's a compiler doing it for us. I will explain a bit later on that. But again, how is actually software separation or hierarchy is actually mapped to the underlying hardware. So here is an example of our integrated graphic architecture, which is common to discrete as well, can be applicable to discrete. So as you can see here, we have subslices, right? Which consists of 8 execution units. And each execution unit has 7 or 8 threads, and it has a CMD possibility to execute each thread in CMD way. And each subslice also have a shared local memory, which is shared across all execution unit inside this subslice, but it's not shared with our subslice. So what's the main idea? So we need to map our workgroups to these subslices, right, in the more efficient way. And the more efficient way means that we need to make all the execution units on GPU running, right, doing some useful stuff. So utilization of this execution unit is important. And if some execution units are wasting the time while waiting for the data, for memory operations, or simply not utilized, then the code is not efficient, and you need to fine-tune this. And this approach with ND ranges and the control of a workgroup sizes, local sizes, possibility to set the local sizes, it gives you this option to fine-tune the code. So here you can see that all work items in the workgroup was handled to one compute unit, which is called subslice in our architecture. And for subgroup, it is mapped to a vector hardware inside each execution unit. So a few words now about the the logical memory hierarchy. As I said, there is always a global memory available for work group, and there is a local memory which is called SLM, shared local memory, available for each work group, and each work item may have its own private memory. So in our case, a shared local memory is limited by 64 kilobytes for each work group. And it's as usual. So if you operate with registers in your code and work item use the registers, it's the fastest one. Then if you want to avoid going to the global memory, which is slower, you can write your code in a way to use the local or shared local memory and so on. Or you can use the subgroups for some operations, which will help you to avoid the usage of a local memory sometimes. So the basic parallel concept was kernels, which we used. It's a parallel 4 with a range class usage. It was quite easy to program, right? But it doesn't allow a performance optimization, because in order to fine tune for underlying hardware, you need somehow to specify the sizes of work groups. And in that case, the ND range kernels allow you to do this. So let me show on the example how it looks like. So in case you want to fine tune the performance, and I would recommend you that you can start with using a simple range class as a beginning, and then further for fine tuning the performance, you can switch to the ND range, where you explicitly specifying the global size, the global iteration space, and the size of a work group. So in this case, we do have the iteration space equal to 1024, and we are setting that we want our local size to be 64, which means each work group will consist of 64 work items. Yeah, what the compiler is doing for us when we specify the range class and not ND range is that it decides how to divide your range into a global and local sizes. So it's not your choice, it's a compiler choice in case of a regular range class. And for ND range, it is option to control it from the software side, from a programmer's side. Earlier I said that there are different ways how to invoke the kernels. So we were focusing on this H parallel 4 with the range class passed as a first argument, right? But it's also possible to execute the kernel only on one single work item using a single task, or you can execute with this explicit ND range we talked a bit earlier, where you can specify the ND range, and some features will be only available for ND range form. So this explicit ND range, for example, this controlling of a shared local memory is possible only when you invoke the kernel with the ND range way. And the last option, but actually some other member functions inside the common group which you can invoke, and they are not focus of this presentation, but you can check the implementation to see what else you can invoke, like fill method and others. And this last one is called hierarchical parallelism. Even by the SYCL 2020 standard, it's not really recommended in this way. It's not really recommended to be used right now because the work is still in progress on how to improve it. But the idea of hierarchical parallelism is that it's a synthetical sugar. So it is actually this parallel 4 with ND range, but simply written in the different form. So written in the form of a nested loops, where you have the outer loop which iterates over the work groups, and here it's an internal loop which iterates over work items. So the kernel function is executed once per work item here and once per work group here. So it's just a different syntax, maybe more convenient for CPU programmers, so for those who used to program on CPU. But I wouldn't recommend to use it at this this state. So since it has many limitations still. Okay, now a bit about the synchronization, because it is important. So when actually the copy data happens, and it's a valid question. So when actually the copy data happens in our hello world example. So in reality, it is not possible to say when it happens with a buffer approach, because with a buffer approach, we don't have an explicit control on the exact moment when it happens. So they have only knobs and options how to control this, right? So what we can do in order to synchronize the host and device communication and then process of a data copy back and forth is we can call a wait member function on the queue, on the device queue. And in that case, we will block the execution and wait until all the kernels, all the common groups submitted to a queue are finished. Then we can use the buffer destruction to synchronize the data. We can use the host accessor. And also, as we already learned, this DAG, the asynchronous graph construction, also controls and synchronize the execution, but implicitly. So inside the kernel, you can only do barriers and memory fence for synchronizing work items. So now on the host accessor, what is the host accessor? You have seen that when we create an accessor inside the common group, it allows us to access the code inside the kernel, like in this case, right? But if we do create an accessor in the application scope and not in the common group scope, then in this case, we are blocking the execution. So it's a blocking call, which will only return after all enqueue DPC++ kernels are finished, which are modifying the same buffer, of course. You need to be very careful with the host accessors, because by using it, you can get a case when the deadlock happens. So I wouldn't recommend it, but it's one of the way how you can do the synchronization. One point which I missed earlier is that the execution of a DPC++ happens in asynchronous mode, which means that once you do the queue submit operation, the execution still continues. So it doesn't block here, right? You can have some host code here written, and it will be executed in parallel with the code, with the kernel written here, right? So keep this in mind, that the default mode of execution in SYCL is asynchronous, so it's not blocking. And most of operations are not blocking. Like later we will talk about memcopy operation, explicit memcopy with unified shared memory, and they are not blocking as well. So host accessor is one way to do this synchronization. The other way is a buffer destruction. And in the original sample with the hello world, I outlined that I have created the additional scope there. And in the same way it happens here. So once we created the queue, we are passing this queue as an argument to this function. And inside this function, we are creating a buffer and doing the submit operation. So once we exiting this this function, the buffer destructor is called. And the destructor of a buffer guarantees you that all all the kernels which operates with these buffers are finished. So we are waiting for all kernels, for all common groups using this buffer to finish before going forward. So that's how, once we exiting this DPCPP code function, we are free to operate with our initial vector V in this example. So we are close to the end of this big first part, and I just want to say a few words about error handling. But again, error handling is based on C++, which means it's based on exceptions. The exceptions can be synchronous and asynchronous. And in most cases, you should expect synchronous exceptions in your code, but asynchronous may still happen because some faults may happen in a common group or a kernel execution, but in that case, the execution still happening because the idea of DPC++ is asynchronous execution. And in order to catch these, you need to use an error handler function, while for synchronous exception, you're using a classical try and catch block in DPC++ code. So this is a way how to catch an exception in case of synchronous exceptions. For example, for construction of an object, like creating of a buffer or creation of a queue, if an exception happens, it will be thrown immediately and you can catch it. And for asynchronous, if some crash happened during the execution on the specific device, you need to create an asynchronous exception handler and to pass it as an argument to the queue. So when you create a queue, you can pass the exception handler as an argument, and you can create it in the form of a function object or a lambda, like in this example, and catch whatever you want. If you want the queue to generate an asynchronous exception, then you can also invoke this wait and throw asynchronous, and await, wait and throw methods to stop and wait until the execution of a queue and all the kernels is finished, and to throw an asynchronous exception if you want. If you don't catch this yourself, right, it will be some default exception handling of synchronous and asynchronous exceptions in your code.
Igor, there's two questions. One question is back to your previous slides with the exception handling, I think, or synchronization. Can I use also future-based stuff to synchronize my application before the buffer destructor, like an explicit wait or get method? The question is about future-based stuff.
I didn't got the idea of this future-based, but yes, you can. So maybe it was.
Maybe the person unmutes the mic and explains the question a little bit.
Yeah, I hope you can hear me.
Yes, yes.
Okay, now it's more in C++, for example, for synchronization, you can have futures to get an asynchronous job done. And at some point you can call, for example, a get method. So the get method blocks until the result is there or the algorithm finished.
Okay. So yes, you can do this as well. So basically all the standard features and even the new C++20 features, which will allow asynchronous execution, they can be mixed. It's only a matter of a host compiler if it does support these features or not.
And sorry, there was another question which probably goes back to slide 31 or so. Maybe Thorsten, you can ask it more specifically.
Yeah, this was about this syntactic sugar on how to write things in groups. And and what I wondered is, I mean, you can do both, but how should I know that the same code is generated, or is the same code generated, or is one code better for one situation or another? It's very intransparent to me.
You mean, what is better, this or that? Yeah,
I mean, either it's identical, but how should I know this? Or one is better, how should I know which one for which situation?
It's again, under the hood, it will be exactly the same code, because
but how could I know that? This is my question. How could I know that this is exactly the same? If I see the one and the other, how should I know that?
It's explained in the specification itself, so that this is actually mapping to the ND range approach. So you, I mean, I don't clearly see the difficulty, but if you see the ND range, which is used explicitly in parallel for when it's using an explicit ND range concept. If you see the parallel for work group or parallel for item, because you see it's a different one, a different method invoked, then it's a different hierarchical parallelism approach used. So this just allows you to write your code in a bit different fashion. For instance, you can declare some data here, and this data will be allocated in the shared local memory. And with the explicit ND range, you cannot do this. You need to create accessors explicitly. So this is only a syntactical improvement, let's say, for those who like the nested parallelism and this hierarchical form. So there is nothing.
Yeah, okay. So it's my personal thing. I hate if there are two ways to do the same thing and it's totally unclear which one to do, because I have no way to decide. I think this is a mistake in the language, but it's so common today, so it doesn't matter.
No, so it was some kind of request for the part of developers who like this hierarchical way, and that's why we created this this feature. But in reality, just stay with that one. So I would say that this is the most universal and powerful way to work with kernels.
Okay, thank you.
So the final talk in this part is about, okay, then where is my hello world is actually executed? And this is a good question. And as I said, it is controlled by the creation of a queue. So in the way how we wrote this in this code sample is just a default constructor of a queue, which means under the hood, it will use the default selector and will pick up some device, which is the most performant from the runtime point of view. So how this happens is that default selector, which is written, so it should be available by standard, and at runtime, all the devices available in your system are ranked in accordance with some logic. For example, like integrated graphics is preferred, has a higher score than CPU, and discrete graphics has a higher score than integrated graphics, and so on. So in that case, some most performant device is selected. You can control it explicitly in your code. So if you want the runtime to choose the CPU selector, when you can pass it explicitly as an argument to the queue constructor. It can be CPU, GPU selector. It can be Intel FPGA selector. Important note here is that there is also host selector, and there is a quite important difference between host selector and CPU selector in the SYCL 1.2.1 standard, because in the SYCL 2020, the host selector is deprecated, so it's not available anymore. But more important is that you can create your own custom selector, which is based on the device selector class, and you can create any logic to pick up the device you want. And in the exercises I prepared on the dev cloud, you have an option to control it yourself. So if you pick up default selector, you have an advantage that you can control the selection of the device at runtime by using the environment variables. So if you set this SYCL device type to GPU at runtime, then the GPU will be used. If you reset it to CPU, then your code, which is written based on the default selectors and default queues, it will run on the CPU. So your kernels will run on CPU in that case. And with the latest oneAPI update 1 package, it will be replaced with a SYCL device filter, which provides you even more options how to control the execution, because in addition to a type of a device like GPU or CPU or FPGA, we also have there may be different devices, right? There may be 5 or GPUs, right? And you need to be able to specify the one which you want. So there will be an option to specify the number of a device, the device type, and the backend too, because it's now more important that the underlying lower level API can be also different, and you can get a different performance. So back to the question about the host device, it is a SYCL 1.2.1 feature, no in SYCL 2020 anymore. And the difference is, by standard, the host device was always guaranteed to be available. So host device, from a software point of view, it's a native execution on the CPU. While CPU device is the device which is available from the lower level runtime. For example, if you invoke SYCL-ls or CL info, it will list all the devices available, right? And you can see that for CPU, you have these OpenCL drivers installed. So if you don't have OpenCL drivers installed for your CPU, the CPU selector cannot select this device as a target one. And obviously there is a difference in the way how the code executes. So with host selector, the code will be executed natively. So it will be bypassing any additional layers, just executing on your device, on your CPU. And for CPU selector, it will go through the OpenCL layer, right? So it is the execution on CPU, but through the OpenCL layer, which probably will introduce some additional overhead, right? We are doing a lot of tests on performance by way of a CPU selector, so on how well the DPC++ code kernels runs on CPU versus, let's say, native oneAPI or native TBB. And I would say that we do have a really good performance numbers. So it's, of course, it is slower, but the slowdown is really small, like a few percents, 5%, and so on. But it definitely depends on the workload and the kernel code. So I also want to highlight one of the main features of DPC++. And as I said in the beginning, it's not a performance portability, but it's functional portability. And it's an option which gives to you as a programmer to decide on which device to execute. So with CUDA, for example, you cannot do this because you only can use NVIDIA GPUs, right? Here, the main idea of a SYCL is that you can target any device you want in one single code. So you can decide which part of your application you want to run on CPU, which one you want to run on GPU, and you fine tune this algorithm for that, or even on any other. And you can mix the devices from different vendors. And moreover, at runtime, there is a possibility that if one device is not available, the execution will fall back to the other device. So there is this fallback mechanism where you can specify the, let's say, fallback queue, right? So if execution on one device fails, then the execution of the same kernel will be executed on the different device, and it's a quite interesting feature. So let's probably go now to this basic DPC++ essential model. I want to share now the whole screen. Okay, I'm doing it. Okay, can you see my screen now?
Yeah.
Okay.
Yes.
So what I wanted to do is to show you is that if you go to the dev cloud, right? I just wanted to show you how easy it can be to get an access, so that all of you can do it right now during the break or even later. But if you're going to the dev cloud, right, which is devcloud.intel.com, here it's Intel oneAPI, right? So it's all you need to do in order to get an access is to fill this quite small form, right? With a name, last name, country, and that's it, and click the button, and you will get the immediate access. You even don't need to verify your email address or something like this. But I would strongly recommend to to enter the correct email address here, because you will get some information how to connect to the dev cloud in the future. Otherwise, whilst the cookies will be will go away from your cache, you will be not able to connect to the dev cloud anymore. So once you follow it, and you can try, it's just a few seconds to finish it, you will get an access to this page. And here, if you switch to the Get Started tab, on the bottom, you can find different ways how to connect with a Jupyter to a dev cloud via Jupyter notebook, and you can run it like right here, or using this link. So if you click here, what is going to happen is that Jupyter notebook is running. I actually already prepared this one, so I will close that one probably. And if you double click on this welcome Jupyter Notebook project, then it will open you the prepared data parallel C++ essential model. So it has quite a lot of different exercises which you can try, and it's not limited by the compiler. So only first 4 modules are talking about it, but it also can show you how you can use Advisor, VTune, and libraries. So, and my idea was to show you at least one module. So let's for example try this module 2, which has all the information which I was talking about earlier. Right, it's like recap of a theory, and then what you can do there is you can play with the code itself. For example, here we do a GPU selection, so you can see that we are creating explicitly a GPU selector, right? And we are passing it as an argument to the queue, and then we are writing to the output what is the device on which we are going to run. So the concept of working with this workbooks is quite simple. You simply select the cell you want and you execute this cell, and the job is submitted to the server and the execution is happening on the server. In addition to that, what you can do is you can go to a file new and terminal and get an access through the terminal. So here you can see that we have all the tools available, but note that here you are running on the login node. So in order to execute, as Michael was showing, and execute this on the compute node, you need to follow the instructions. And you can, by the way, learn all this by following this Module 0 introduction to Jupyter Notebook. So back to our code, as you can see, since we selected the GPU selector here, we are running on Intel graphics. So if you want to modify this code, you can also change this, but don't forget to rewrite this so that the file is overwritten, and then you can go further and build again. So going further, there are different parts what to try in different code samples here. One is talking about ND range and dependencies with accessors and how you can handle this. For example, in this particular code, you can see that there are many different kernels submitted one by one, right? And that the correctness of the code is done by the dependency graph, which is constructed by the runtime, because we are using accessors here. But later on, there will be an example with unified shared memory. And there you don't use accessors. And in that case, you need to care about these dependencies yourself. So if you are going back to this sample I was compiling with a device selector, so it's now running on the Intel Core i9 CPU, which is available on this compute node. And yeah, there are many options how to play with this. And here I plan to spend a bit more time, but I think we have only 20 minutes left, right? Until the break, until the lunch time.
No, 25.
25, okay. Yeah, I will probably show it after talking about unified shared memory, which I think the most important one right now. So I just encourage you to try it because it's so easy to access it. But it's also a lab exercise on the bottom of this module, which allows you to simply follow this code and uncomment some of the lines, like here, uncomment the following lines where you're setting the rating for the device. So this code example is showing how you can create your own custom device selector class, and you can create your own logic. You can see here, you can create your own logic of selecting the device by giving a rating. So like to prefer the GPU over CPU. And what you can also do is you can pass a string of a vendor name as a parameter to the constructor. So later on in the code, if we will go to the main of this code, you can actually construct the queue based on the selector, and this selector you created with your custom device selector class, and you are passing this vendor name as a string. So what is the custom device selector constructor is doing is just checking the name of a device and trying to match the available device. So you can create your own logic and pick up a device based on your own preferences. It may be some kind of unique address of GPU or unique name or the number of a device and so on. Okay, so now I want to go back to the slides and talk a bit more on the way how the compilation works, and then switch to a unified shared memory. So as you can imagine, the code consists of two parts, right? It's a host code and a device code, and we talked on one of the first slides on that. And because of that, we need actually host compiler, which will compile your code to run on CPU natively, and you need to have a device compiler, which can be quite different depending on the device target, right? Target based on the target device you have. But the compilation usually happens in this way. So once you invoke the compiler driver, and we expect it to be DP-CPP, right, driver, but it can be also ICX driver. Again, the driver is only some kind of a wrapper. So finally, under the hood, both these driver names invoke the clang++. So what you can do is you can actually invoke clang++ if you want. Just make sure that you are passing all the required options like -fsycl, -fsycl unnamed lambdas if you are using this feature to avoid the explicit naming of a lambda functions in the kernel's invocations and so on. So it's up to you to decide. But the benefit of using DPC++ is that it has all the required paths set as -I, -L option, and it has all the required fsycl options set by default. And under the hood, this driver invokes as a first step the SYCL device front-end compiler, which generates the integration header file. So this header files has the definition of your kernel code, and it is invoked in the form of a function then in your host code. So this the generation of this integration header file allows you to compile your C++ host code with actually any C++ host compiler. So it can be ICC, it can be GCC, it can be clang. So any C++ 17 compatible compiler, or even C++ 11, I think will work in that case, depends on the features you're using in the code, will allow you to compile the host code, generate the host object, which will finally be used by the linker to generate a fat binary. And for device code, the situation is more tricky. So for device code, we have different alternatives what to do. But as a first step, we generate the IR because it's quite common, right? We need to have some kind of IR to apply the optimizations to this IR and not to a high level language. So we are generating an LLVM IR, and then based on that, we're generating a SPIR-V binary format. So this is not a native instruction set architecture. It is still some kind of intermediate form, right? And then we can decide, do we want to generate at compile time the target architecture ISA, or do we want to do it at runtime once we are going to run our application? Which means if we know what we are going to run, let's say on a Tiger Lake, what we can do is specify following options to a compiler. And at compile time, it goes through this path and generate the target architecture instructions, and finally we'll put it to a fat binary. So at runtime later on, you will not need to compile anything, right? But in that case, you need to run on the Tiger Lake, because otherwise it will fail at runtime if the device will be unsupported. So the alternative, and this is the default one in case of DPCPP, is to use a just-in-time compilation. In that case, SPIR-V is simply wrapped to the object file and linked. So in fat binary, in that case, we have this SPIR-V. And at runtime, once you invoke your application, the runtime will proceed with the compilation, just-in-time compilation of this SPIR-V binary format to the target device architecture. So you need to understand this and keep in mind that there is an extra overhead by default with DPC++ compiler to compile the SPIR-V file. If you don't want this overhead to happen because you know your target device in advance, then you can use this so-called ahead-of-time compilation. And there is a more detailed explanation of a compilation flow here. And you can also Google for ahead-of-time compilation DPC++, and it will show you more data on this SYCL target and -XS option. Any question here? Okay. Yeah?
No.
Okay. So then what is happening at runtime? At runtime, as we've learned, we may have our host code, right? And we may have a device native ISA, or we may have a SPIR-V. So it's this or this, not both of them together. It's option number one, and it's option number two, depending on which compilation mode we've chosen, right? Again, I said that DPC++ and SYCL is an abstraction. And abstractions means that you will have different lower levels and layers under the hood. And this is what is happening with DPC++ applications. So on the higher level, it's your SYCL code. Then it's basically goes to some lower level implementation with the help of a plugin interfaces. So in reality, all this DPC++ code is mapped to some kind of lower level API. And in the beginning, it was OpenCL code. But nowadays, you can choose what will be the backend technology. So it can be OpenCL, it can be level 0, and it can even be a CUDA layer. I haven't put it on this slide since it's in open source compiler only. And note that the performance using these different layers can be different. So the behavior itself can be different, and the target devices can be also different for different plugins and backends. So for example, we targeting level 0 for Intel GPUs, but in reality, for level 0, we have an open specification available under oneAPI spec. And there you can find that it's by specification, it's not limited to Intel GPUs. So any vendor can take this specification and implement their own level 0 lower level API and lower level plugin. OpenCL at this moment is able to target Intel GPUs and FPGAs and CPUs. So from that point of view, it's more diverse, right? What else to mention here is that you can control which backend to use or which lower level API to use at the runtime. So you can use this SYCL_BE environment variable, but I said that it will be replaced with this. So this SYCL device selector and SYCL BE selector are both merged into one unified SYCL device filter in the latest version of DPC++. And open source, it's already available, by the way. And with that, you can devise, do you want to run with OpenCL layer, level 0, or even CUDA layer? And in order to make this abstraction, right, the feature called plugin interface layer was introduced. So in reality, during to make this mapping of high-level DPC++ code to low-level OpenCL level 0 CUDA code, in order to make this mapping, you need to have some intermediate plugin interface. So in reality, it first maps to some PI APIs, and only then at runtime, we are building a dispatching table and executing on the device we want. But yeah, please refer to this for more details. It has a lot of information on how it is implemented, so that you know what is happening under the hood.
Yes? Igor, can you go back 2 slides? There's a question from the chat about the target-specific compiling path. Can you set multiple targets to generate at compile time to avoid the JIT compilation,
yes.
but have multiple options to choose for the devices?
Yes, it's possible. So here you can just list all the devices you want, and it will generate your code for different devices, or even, so this is actually -XS, it's passing this option to a target device compiler. So you can devise it for different one, but even here you can generate different targets. So yes, it is supported, and it will be just a very fat binary in that case, right? So it will consist of a different code path which you can execute. Yes, it's possible. Okay. Even more, we have many improvements on that, how to allow this compilation from a code level at runtime. I know what this is happening, but it's more in depth. It's simply to use ahead of time compilation at this moment. By the way, it's a very good hint. If you do see any issue at runtime with the compiler, then try the offload compilation, offline compilation, try the ahead of time compilation to see if the same issue is observed at compile time, because it's always better to have a debugging of problems, right, of your code, bugs or whatever, at compile time than at runtime. It's easy to catch this, right? Okay, so yeah, motivation of why USM is important. So USM would be one of the first really major features from SYCL 2020 I would like to talk about. And motivation is that this abstraction model with buffers is really great, but to simplify the porting of a code to Accelerator, right? Or even moving from CUDA to DPC++, it's also one of the point here. It's important to get this simplified way of explicit control over the memory copy operations and so on. So it's not a, so I heard the point that if you do have 2 options, it's hard to decide what to choose, but here it really depends on your needs. So you really need to have both of these. And both concepts brings advantages and disadvantages, pros and cons. But from the developer's point of view, the unified shared memory looks like the picture on the right-hand side, so that the pointer which you operates on CPU, right? It's points to the same memory address, so you can use the same pointer from both sides, from CPU and GPU. And this is what unified shared memory allow you to do. And there are different ways how to allocate the memory. There are different allocation types you can use. It can be the allocation on the device. It can be the allocation on the host side, and it can be so-called shared allocation to implicitly control the memory operations. And depending on these allocation types, you can access this pointer on the host side or device code side, or the data actually can even migrate because host and device. So let's go further into the examples showing it in more details. So we've seen how it works with buffer and accessors, right? We create a queue, and then we have our data, and we need to wrap it to a buffer and use accessor inside the kernel. So what USM allow you to do is to allocate the memory explicitly from the host side on the device, like here. So you are just saying which size of a chunk of a memory you want to allocate, and you are passing the queue as an argument. You can also pass not the queue, but the device and the context as a parameters. It's also possible. Then the memory initialization happening on the host side, and then we explicitly doing a memory copy to the device. Then we are blocking in order to be sure that this memory copy operation is finished. And going forward to invoke a queue submit, so far looks quite similar to what we had from the queue submit point of view, but you can see that in the command group scope, we don't have accessors definition anymore. So what we are doing is simply invoking a parallel for and passing the lambda function with the kernel code. And here we are using the device array, so the pointer, which we allocated on the host side. We are using it in the device code. And after that, we are doing the synchronization. So we are waiting until the execution of this kernel finished, and then doing the mem copy back from the device to the host, waiting again, and we are free to operate with initial host array. So back to a question on when the copy, memory copy happens with buffer and accessors, we don't know for sure, right? Only on the synchronization points like Q8 and so on, we know that the memory copy is happening, but we don't have a control on when to copy it to the device. So it's more or less controlled by the runtime, and there are additional features in SYCL which can allow you to do it more or less explicitly with buffers. But again, for that kind of stuff, if you want to control explicitly the moment when the memory copy is happening, then you need to use the unified shared memory. And it is expected to be the most performant way. I mean, for the best performance, you need to control it yourself. We definitely rely on our smart runtime, but this is an approach for the fine tuning. Yep. Any question?
Igor, if you go back to the slide, the host allocation type is confusing, that is accessible from the device.
Yeah, it means yeah. I will have an example further. Okay.
Okay.
Let me show this implicit data moment. So here we do allocate the host memory with malloc host, right?
Mm.
And we are using this host array inside the kernel device code. So it is accessible. I mean, you can use this pointer inside your device code.
Okay.
So this is an alternative approach where you don't need to care about mem copy operation. So it's called implicit data movement, right? And in that case, we are using so-called shared allocation. And this shared array is also used inside the device code, right? But it is also used in the host code later on. And you can see that in that case, we are not doing explicit mem copy before Q submit and after that. So only what we are doing is just a Q8 to be sure that execution of a kernel is finished before printing, before doing this assignment back to the host array. So this is implicit data movement. When to use it? The recommendation was to start with this implicit data movement because it's easier to migrate to this approach, and then to fine-tune the performance for some kernels via this explicit data movement. So moving forward with explicit control. But there is one disadvantage with USM is that once we don't have accessors, right, we cannot rely on the runtime to track the dependencies between the kernels. So you need specify explicitly the dependencies between kernels in that case. And you have different ways how to do this. You can invoke the queue-wait, you can wait on event object, or you can use depends on method inside the common group. And I will explain now. So now there will be some details on what is better and what is blocking and not non-blocking. It's quite important. So in this particular example, we do have a queue. We allocate the malloc share. So we are following the implicit memory USM. We are initializing it. And then what we are doing is we are performing a queue submit operation, right? And this is, I intentionally named it as a task A. So this is this kernel, right? So then we do have one more queue submit and one more. And you can see that inside we are writing to the same data, which is actually a possible issue, right? Some kind of data race. And we need to execute these kernels one by one. We cannot execute these kernels in parallel. But once we don't have accessors created here, we need to care about ourselves. And what we are doing, it's the worst solution is to call the wait function. And it's worse because wait function is a blocking function. So it will block the execution of this code, and the host code, which may be available here, right? It will not be executed until wait is finished. So the better idea is to do it based on this depends on method and events. So what you can do is you can create an event while submitting a queue, a common group to a queue. And then you can specify inside the common group scope that the execution of this kernel, of this kernel B, task B, depends on the execution of a kernel A, so that we cannot proceed with the execution until this one is finished. Why it is better is because it's non-blocking execution. So it means if there is some host code here until the next queue submit, it can be executed. So the runtime will schedule the execution itself, but the execution from a host code will continue and will be not blocked. And the third option, there will be even more, but the third option is to use the in-queue, in-order queue property. So it's not in queue, it's in order property for the queue. And this option says to the runtime, okay, any kernel or any common group which we do submit to the queue should be executed one by one. So it's sequential execution of the kernels. In this case, it's also non-blocking execution, but it's, the granularity is the whole queue. So all the kernels will be executed in this way. By the way, if you will create two separate queues, which are both in orders, then you can still make it possible to execute these queues in parallel. So you are not limited to only one queue. You can create as many queues as you want. Just be careful with that, because the creation of each new queue leads to results in the creation of a new context, and each new context requires the recompilation of a kernel. So if you want to use multiple queues in your code, it's much better to pass the same context into that. But And the final example here is showing that actually you can execute some kernels in parallel if you don't have data dependency. Like in this example, you have data 1 and data 2, both allocated with malloc shared, and you're writing to one data in one kernel and to data 2 in the other kernel. So there is no dependency here. So in that case, you can simply execute both of them in parallel and then specify by using the depends on that C need to wait until both are executed. Or you can, this is one way how to do this, and there is an alternative way, is that you can specify both of these events as an argument to a parallel for. So here you can see that we are just passing both of them as a second argument to a parallel for. And it's the same functionality, just a simplified way. So I think that's it for today. I don't want to go to the subgroups to save some time, and want to show you, so first of all, any questions on unified shared memory?
There is none on the chat so far.
Okay. So let me go to essential models again. So there is a dedicated for unified shared memory module there, showing the use case of USM. It's again, there is a recap of a data there. So let's briefly go over the examples available there. So one is, by the way, it was missed on the slides, but it can be sometimes useful to check if the device actually supports the unified shared memory. So there is a way in this get device, get info member functions to actually check if a device does support unified shared memory, because it's possible that some devices simply doesn't support unified shared memory. When we do this for target device, but it's better for the correctness of a code for any target devices. So it's malloc shared, as was shown earlier, and we are just performing this operation and explicitly wait here, and then printing the data results. So I was, while passing this tasks, I sometimes was intentionally doing some mistakes in order to see what will happen, for instance, if you don't synchronize. And it's an interesting thing. So here it's as an example with in order queue. So in that case, you don't need to implicitly synchronize. But the interesting thing I found was here. So there are 3 tasks which submit without data dependencies, you see, and it actually requires a fix here, because there is definitely a data dependency here, because we are writing to the same array, right, which is allocated, but we don't synchronize anyhow. So we can do it in the different ways. We can use an events, right? We can do a queue wait, but it will block the execution of a host. But the funny thing that I executed this and the results was correct. And you shouldn't rely on that. But to understand this behavior, you need to know that under the hood, right, all these functions, they go to some lower level API, and finally they go to some even hardware level API, right? And I've just learned that for Gen 9, for example, and it's running on Gen 9 in this example, the compute runtime and the memcopy runtime was not parallel in the software stack. So that's why in this particular example, running it without synchronization worked as well, but it doesn't mean that in the future it will allow you to do this. So be very careful and make sure that you are synchronizing before next kernel is started to execute, and after each memcopy operation, which I explicitly ordered. For instance, okay. For instance, in this case, we are doing the explicit synchronization by creating the automatic events and by passing these events as an argument to a parallel for. And then running this code leads to a correct results. Okay, I think that's it for today. I hope that you are motivated to try this yourself, and it will be interesting to hear your feedback. And yeah, feel free to ask any questions during the day later today. And the next session will be more on DP C++ compatibility tool.